Again, as I mentioned, if you have questions, feel free to interrupt me. One of you did that, and that was very good because that part of the complexity was not something that I had intended covering, and that gives you another level of complexity that's in the DNA analysis, as you can imagine. That makes things even harder. Okay, so as you can see, I retitled this part of the lecture as Lecture 3B. Now we're going to focus on challenges and opportunities, but the previous part of the lecture was really a motivator for this from just one application. I could do exactly that same motivation for machine learning, for graph analytics, for databases, let's say, for many, many applications today, actually. Although maybe it won't be as exciting as genomics, because genomics is something where we don't have a lot of answers to put, and we have many, many questions also. And we sometimes don't have the questions to ask because we don't know what will come in the end. So there will be many, many more questions coming. Basically, if you dream of these high performance energy efficient devices for genomics or other key applications, in genomics at least, if the requirement is real time like this within a minute, then we're very, very long ways to go from there. Today, devices don't have computation capability. So basically, we need to solve a lot of problems. In the end, we're bottlenecked by memory. And I will argue that at some point, security and privacy is also bottlenecked by memory, because if everything stayed in your memory and never went out, and it was basically kept secret, then maybe you wouldn't have a lot of security and privacy problems, because you could constrain things to a particular device and location. The problem happens, data moves around, and while the data is moving around and being processed on, information gets leaked from that data to people who should really not have access to that information, right? So data movement is actually a security problem as well, and a privacy problem as well. If we can somehow constrain the data movements by solving the memory bottleneck, we can potentially improve the security and privacy of our devices too. Okay, so I think solving the memory problem will help us solve a lot of these, as we've discussed. We want security, reliability, safety, energy efficiency, low latency, and predictability, and hopefully enable architectures and applications and whole systems for interesting workloads and future devices. So that's why we're going to focus a lot on memory and storage at the initial part of the course. So let's start with some motivation. Why is memory so important today? I've given you the application perspective. Memory has always been important, but especially today, we're very critically bottlenecked by memory. And as a result, there's a lot of innovation that's going on in industry, as you have seen in the last lecture, where we talked about Cerebras, for example. They were motivated by putting memory and computation together. UPMem, for example, who are doing in DRAM processing. Rowhammer is another example. So we're going to talk about this. Basically, there are multiple perspectives that we're going to talk about. One is the performance perspective. Performance is always important, of course, regardless of what naysayers say, as we have briefly talked about earlier. Energy is critically important. Scaling, reliability, and security, they're all critically important. So I'm going to give you these three perspectives, some of which we already discussed, but some of which we're going to delve deeper into. And then we're going to talk about trends, challenges, and opportunities in main memory as part of lecture 3C. Let's see if we get there. So this is a traditional system, and main memory system is really a component of all systems that we design today. It's whether you're designing server, mobile, embedded, desktop, sensor, some sort of accelerator, main memory is a big part of it. It's a critical component, basically. It sits in between processors and caches and the storage units, although, as we will see, there's an opportunity to merge at least the next level of storage with main memory. But of course, there could be other levels of storage, right? There could be tape over here, for example, in data centers. Tape is being used for archival storage today. It's really old technology, but it's a robust technology in the end. It's very, very dense. And on this side, there could be other stuff also. Whether you're designing processors and caches or FPGAs or GPUs, as I will show you in the next slides, you're bottlenecked by memory. Basically, let me actually show that right now. Everything goes through main memory, basically. And at the end of this lecture 3B, you will see a picture where you have a modern system on a chip. It's a cartoonish picture. But in a modern system on a chip, all of the components, different accelerators, different pieces go through main memory, and they go through the memory controller. So in the end, memory controller and main memory becomes a bottleneck in these systems. Even if you don't have a lot of components, a single CPU and a single main memory, not many systems are like that except for IoT systems and microcontrollers today. But if you have that, still main memory is a bottleneck if you have a data intensive application. So if you want to maintain the performance growth and technology scaling benefits that we've been used to, if you want to basically improve performance, the memory system must scale. And it must scale in multiple dimensions. It must scale in size, capacity, technology, efficiency, cost, and the algorithms we use to manage it. And we're going to look at essentially all of these aspects in this in the first part of the course. So this is another cartoonish picture that I have. This is memory system. I actually drew this picture in 2008 or so. I was writing a position paper for actually re-architecting the computer architecture curriculum at Carnegie Mellon University. And that's one of the reasons why I drew this picture. I was also writing, I used also in a grant application to National Science Foundation saying that this is an existing system. Existing systems have not changed as much since then. But basically, you see that most of the system is really dedicated to moving and storing data. So let's take a look at these components. So the cores, the red things over here, are doing computation. Okay, those are the computational units. They're connected with some sort of interconnect, which is moving data. They're connected to L2 caches that could be shared or private. It doesn't matter. They're storing and moving data. There are other shared caches over here that are storing and moving data. There are shared memory controllers that are orchestrating the data movements and storage, etc. There's shared memory storing data, and there's shared storage, other interconnects. You can see that if you look at a single node today, not more than 10% of the hardware area is dedicated to computation. When I say computation, it's think of arithmetic logic unit, for example. Think of pipeline structures, for example. Not more than 10%. And 10% is actually, if you include the storage device, for example, okay, let's assume that we don't even include that. If you include a large chunk of memory, 10% is if you're lucky. Usually it's 5% of the hardware area you do computation in. It's a bit sad, right? We call these systems computing systems, computers. But if you look at the hardware resource area that's dedicated inside, only a very, very small fraction goes to really doing computation. Everything else goes to data movement and storage. And maybe we should be calling these data movement and storage units, right? And in fact, if you go into the core, this red part over here, and deconstruct a little bit, much of it is really not dedicated to computation again, right? What do we have here? We have an L1 cache. We have a register file, or multiple register files, actually. They're all memory in the end, and they're interconnect also connecting them. So even a good chunk of this processing core, as well as the accelerator that I showed you, you saw the GenASM accelerator in the previous part of the course, it's a significant chunk is really dedicated to storing data, buffering data, moving data around, interconnects and buffers and register files and L1 caches and specialized buffers, for example. Basically, the takeaway is memory system is a big component of a computing system today. And if you throw me an accelerator, it's the same thing. If you throw me a GPU, it's the same thing. A GPU has huge register files, for example. Register file is a big complex part. It has large scratchpad memories, large caches, huge memory controllers again, and unfortunately not as big off-chip physical memory. It should really have bigger physical memory today, but hopefully that'll get solved also. But basically, the story is the same in different compute devices. As a result, my picture has not changed for 11 years or so. Okay, the other comment that I'm going to make over here is, and I will also say that this is because of the paradigm we're designing systems today, because we're really processor-centric. Everything needs to move to the processor before it gets processed. The shared cache doesn't have processing capability. The interconnect doesn't have processing capability. The memory controller doesn't. The shared memory doesn't. The storage device doesn't. No one can do processing other than the red cores over here. And because of that design, I think we're very imbalanced, in my opinion. We're going to talk about that, especially when we talk about computation and memory. And that's the reason why companies like UPMAM and Cerebras are actually trying to change the way things are done so that we're not bottlenecked as much by memory. Okay, so the second key point in this picture is the memory system is really a shared resource across these cores. So these cores may be running a single parallelized application or multiple different applications like a cloud computing scenario like we discussed in the previous class. Doesn't matter. The memory system, the interconnect caches, etc., it's shared between those cores, which means that as we discussed earlier, when we talked about memory performance attacks, when one core is trying to access one resource, the other core may be denied service to it. So this is a big problem. It's a quality of service predictability problem. And we're going to talk about that in later parts of the memory lectures, not initially. But keep that in mind. And I'm going to talk about that as a challenge today also. Okay, so 2 key takeaways from this picture. Most of the system is dedicated to storing and moving data, even though we call these computers. And most is a really large most, like 95% or so. And the second is memory system is shared across cores or accelerators or a heterogeneous combination of cores and accelerators, which means that it becomes a quality of service and predictability bottleneck. Okay, let me give you a one-slide overview of the state of the main memory system as I see it. There are some recent technology, architecture, and application trends that lead to some new requirements and that exacerbate old requirements. We've always demanded a lot from the memory system. I'll give you a historical perspective also in this course. An architect looks backward also as we discussed. So there are always a lot of requirements from the memory system, but there are going to be even more requirements going into the future, as I've discussed with from examples with genome analysis earlier. And we will discuss some of these new requirements also. And we're going to talk about these gradually, if you will. If, for example, a new requirement could be the memory system should supply data no more slowly than, let's say, I don't know, 2 nanoseconds, so that I can do all of my analysis within a minute. Right? That's a good requirement. The memory system should supply data with no less than, I don't know, 1 terabyte per second bandwidth, such that I can finish the task that I have in the software so that I can meet my deadlines when I'm doing the sequencing for COVID-19 in the field. And of course, while doing that, it should really not consume more energy than, I don't know, 0.05 picojoule per bit. That's a very low number, by the way. Okay, so these are example requirements driven by applications, but there are also technology requirements like scaling, as we will discuss later on. And actually, I've assigned a required reading from a book chapter that I've written. It's called Memory Scaling, Challenges and Opportunities. It's hopefully a nice book chapter that talks about essentially what we're covering in these lectures. We don't have an assigned textbook, but I'm going to use some of the papers and these book chapters that we've written, which are essentially parts of books that will be useful to actually follow the lectures, and you can go into more depth in terms of something that can help you actually to read in more detail. So that chapter is already assigned as part of homework 1, and I recommend reading it because it will help you make even more sense out of these lectures that are coming. Okay, so I will posit that and hopefully show you that DRAM, which is the main memory technology that we've been used to for decades, which was invented in 1965, and memory controllers, as we design them and know them today, are already failing to satisfy all of these requirements. For example, Rowhammer is one example we're going to talk a lot about. This is a failure that is not so good. It's failing to satisfy the basic reliability and security requirements. That's one example. And I'll show you more examples as we go along. And also there's some opportunity. Basically, there's some emerging memory technologies that happen to be non-volatile, like phase change memory. They enable new opportunities, and they could be satisfying some of the requirements, although they could be taking us worse in some other requirements. So some opportunities are, because you have non-volatility in your memory, the data doesn't go away when you pull out the plug, when you actually don't have electrical power. You can actually use these memory technologies as both memory and storage at the same time. And that enables new opportunities, as we very briefly discussed when I introduced Intel Optane memory, which is an example of phase change memory. So given all of these trends, and given all of these interesting opportunities, it's a good time to rethink the main memory system, such that we can fix potentially the issues we're having with DRAM and enable some of these emerging technologies while satisfying all the requirements from applications, architecture, and technology. So you're actually having this course in a very good time, because this slide wouldn't have made any sense in 1990s. I've already given you the historical perspective, but I couldn't have put up the slide in 1990s, for example, even in early 2000s, I think. Well, in 2010s, I was using the slide actually. So early 2010s, 2009s, I actually constructed this sort of slide. And I think for some time we will use the slide, because I don't think the main memory bottleneck is going to go away anytime soon. Okay, so let's talk about these major trends affecting main memory. Again, this is in one slide over here. So basically, the first slide is about really about performance and predictability. We want more performance and more predictability, more quality of service from the memory system. The second one's about energy and power. The third one is about technology scaling. Okay, and you will see that some of this is driven by applications, some of this is driven by both applications and technology, and some of this is driven by technology itself. So okay, let's start with the first one. Basically, we want more capacity in terms of memory. We want more bandwidth. We want lower latencies. We want better quality of service. We want more predictability. Basically, we want it all. If you've taken my digital design and computer architecture course, when I started the memory lectures, we started with ideal memory, right? Ideal memory is zero latency, infinite bandwidth, infinite capacity, and zero cost. I didn't have the quality of service requirement over there, but if you have zero latency, infinite bandwidth, predictability becomes goes away, basically, infinite capacity also, of course. Basically, we want to get as ideal as possible. But of course, as you also know from those lectures, it's not easy. It's a trade-off space, right? Capacity and latency are fundamentally opposed to each other, right? And we will discuss that actually in this course. This is very fundamental on any type of memory. If you're building a register file, you will be bottlenecked by that. Basically, everything that I discuss within the context of main memory applies to any type of memory structure in the end. All of these we want from any type of memory structure in the end. But main memory is such a huge bottleneck that we really are constrained in main memory right now that we wanted earlier perhaps from other parts. For example, in the register file, we don't have as big of a capacity problem. We don't have a bandwidth problem because it's on chip, although ports are a problem, clearly, so there could be bandwidth problems, but it's not as bad as main memory today. Okay, so why do we want all of this? First of all, I will posit that computation is not a big problem. That's why we're starting this course with memory. Computation, hopefully you covered in some of your lectures, some sort of digital design course. You designed some sort of simple processor. You may have designed some sophisticated processors. If you've taken my course, for example, you may have learned about them. But basically today, we know how to build computational agents really well. We've optimized a lot out of them. A general purpose processor is good. Accelerators are good. GPUs are good. We know how to build them really well. We know how to make them multi-core. Basically, we can put many cores on chip. We're really limited by main memory, as I will show you in the next slide also, actually, next few slides. Basically, computation is not a problem today. We can design these multi-core or multi-agent systems really well. The difficulty is over here. And as a result, once you increase the number of cores, once you put many cores, they demand more memory capacity, they demand more bandwidth, and they cause more quality of service problems by actually interfering with each other. Right? So multi-core is a driver of this trend. Basically, multi-core is just one example, actually. It's really multi-agent systems. You have heterogeneous systems today with lots of accelerators, cores, etc. It's really the fact that we are able to do computation units extremely well in current technology. We've really mastered it. That is really making the memory bottleneck today. Okay, that's number one over here. The second one, applications are becoming increasingly data intensive. And I think there's nothing else I should say after the prior lecture that talked about genome analysis over here. There's a huge demand and hunger for data. Machine learning is a prime example of this. Basically, there are people who want to analyze all your data for good or bad purposes, clearly. Hopefully, more good purposes will prevail in the end. But there's data, it's out there, it's being produced at much larger quantities than we've ever been used to. It's going to continue that way. Applications are increasing data intensive, and people want to do something with it in the end. So this is driving capacity, bandwidth, quality of service, every requirement up also. And the third thing is, we also discussed this, consolidation is important. Basically, we want to consolidate more and more. If you have a chip, if you have a data center, this consolidation is happening at multiple levels. For example, it's happening at the chip level, it's happening at the unit level within a chip, it's happening at a board level, it's happening at a rack level, it's happening at a data center level. Basically, we want to consolidate more and more applications to a given piece of hardware such that we can most efficiently utilize that hardware. We can maximize the efficiency, and we can minimize, we can basically minimize the power overheads overall. We can maximize the area efficiency, we can maximize the cooling efficiency, we can maximize the building efficiency in a data center, for example. If you consolidate more and more, run more applications at the same time, that's good for all of these purposes. But this drives the trends for main memory capacity up. You want more capacity now in a single node. You want more capacity in a data center. You want more bandwidth. You want better latency, better quality of service, better predictability, etc. This is also happening in GPUs. GPUs are running multiple kernels today. They're going to run multiple applications, and they're going to be even more sophisticated going into the future. Mobile systems also, heterogeneity, etc. Right? So these three things are really driving the requirements up. So let's examine some of these things. So let's take a look at actually the memory capacity gap. This is from a paper that was written by HP Labs and the University of Michigan. It's a nice paper. It was published in ISCA 2009. You can read it. It's going to be part of the reading list for this lecture. But basically, these folks have done some analysis in 2009, and they basically looked at just trends. And they found out that the core count is doubling approximately every 2 years, and DRAM capacity is doubling approximately every 3 years. So they call this the memory capacity gap. They basically said memory capacity per core is expected to drop by 30% every 2 years. Okay, assuming this is true, this is not good. Why is it not good? Because the software usually expects, if you don't assume that you don't change the software, a software usually expects, as it grows, it expects more memory capacity, basically. And this is a vicious cycle in a sense. Software always expects better hardware over time. Software revolution is based on hardware innovation in the end, how fast the hardware provides performance. And if you don't get memory capacity, that means that either you're going to run your multi-core system less efficiently, basically you're not going to use all your cores with demanding applications, or you're going to be even more heavily memory bottlenecked, basically, because you don't have enough capacity for the software. Or you need to rewrite your software completely such that it can make more out of less memory. So that sounds like actually even worse, perhaps, right? Because a lot of the software designers, let's say about no more than 90% of the software designers don't even care about how much memory capacity they have. Virtual memory is there for that reason, as we've discussed again in digital design and computer architecture, right? So basically, this is not good. This memory capacity gap is going to put burden everywhere. Okay, that's assuming this figure is true. Okay, you can always argue whenever a figure is thrown at you, critical thinking, it's always good to think critically. Is this figure still valid? And I don't have the data, but I suspect it's valid in especially a domain like GPUs, for example. In GPUs, we're adding many, many more systems, many more cores, for example, and we're not adding a lot of memory, unfortunately. So basically, you have a lot more computational capability today, and that's increasing much faster than memory capacity is doubling. So that's a bit unfortunate. So the trend is continuing in GPUs, in my opinion, maybe even getting worse. I don't know. I don't have the data, but based on my insight into the field, I believe that in GPUs, that's true. Maybe some of you will be interested in actually draw this figure for GPUs. And I believe as you add, if you look at the computational units, maybe not necessarily just the cores, but if you add the other computational units that we add into the system, machine learning accelerators, other accelerators, GPUs, other heterogeneous accelerators, image processing accelerators, audio processing accelerators, DMA accelerators, etc. If you add all of them into the system, they're also growing in terms of their computational capability, but DRAM is not growing as fast, in my opinion. So that's another study to do. Basically, if you look at a heterogeneous multi-agent system, and if you consider those as cores, and I would suggest computational units is a good way of looking at it, or computational capacity is a good way of looking at it. The question is computational capacity versus memory capacity, right? How are they growing? And I believe the computational capacity of our systems are growing much faster than memory capacity today. Okay. And I think my last point over here is, okay, assume that that's not true. Assume that this picture is not correct today. Then it's always a good question to ask, why is it not correct? Meaning that, okay, maybe in the general purpose domain, the core count is not growing as fast today. I believe it's growing actually surprisingly, but the general purpose cores, let's say that it's not growing as fast. The question is, why is it not growing as fast? Well, maybe they're bottlenecked by memory, and who in the right mind would actually put more cores if they know that those cores are not going to get the memory capacity they need, right? And I believe that that's actually the case. In fact, there were trends in memory multi-core. Initially, when multi-core was introduced, people were actually excited about putting many, many cores on chip. Okay, and then they reduced the number of cores they started putting on chip, because they quickly figured out that these cores are bottlenecked by memory. What they did was they started putting more cache onto the chip so that at least they would alleviate some of the memory gap with an easy solution. Let's say putting more cache is clearly an easy solution. We know how to do that, right? I mean, it's a patching solution, but that's a reason people use to not double the cores, not increase the cores. So if the trend is not continuing, these things are not independent of each other. The trend is not continuing in some cases because memory is a big bottleneck and it doesn't make sense to add more cores. It's not because we cannot add more cores. We actually have, I don't know, trillions of transistors per chip. If you look at wafer scale chips, we have lots of wafers, as you know. So it's not because we cannot put more cores that we don't put more cores. We don't put more cores because they're bottlenecked by memory. Okay. Okay, so if you actually look at the trends for memory bandwidth per core, those trends are even worse. And I haven't plotted it over here, but I'm going to show you a different picture in a little bit in the next slide, which is this picture, basically. This picture shows the trends in terms of memory capacity, bandwidth, and latency for a single DRAM chip. And we're going to look at the time span between 1999 to 2017. And we're going to look at how much the capacity of a single commodity, most common in the field, DRAM chip has improved, how much its bandwidth has improved, how much its latency has improved. Okay, normally if we were in a classroom, I would ask you the question, but maybe I'll ask you the question. How much do you think the capacity, storage capacity in terms of bits of a DRAM device has improved compared to 1999? Assuming that in 1999 you had 1 bit normalized, where are we today? And this is log scale, right? Any guesses? Let's see if there are any guesses over here. I don't see any guesses. Come on, you can guess something. 90, I see. 64x, that's good. There are some guesses I see. 16. Okay, that's good. I got 3 numbers. Okay, I see some more numbers, 24x, 10x. These are good guesses. Maybe I actually put down a lot the memory capacity, but actually you're all underestimating. Basically, things have improved a lot in terms of capacity, under 28x. And this is good. And it's good that you underestimated because things are more positive than what you underestimated. Basically, the reason is this is really the focus of DRAM chip designers. Basically, they want more capacity. This is really what they designed their commodity DRAM chips for, more capacity. This is what sells. I believe other things sell also, but this is the traditional business model. We're going to talk about the business model later on when we talk about some other things in DRAM. But basically, this is what the chips are designed for. And as a result, capacity has been improving nicely. But of course, we're having problems recently, like Grove Hammer, and capacity is not improving as fast today, actually, compared to around here, for example. Okay, let me get your guesses on bandwidth. How much do you think bandwidth has improved in the last 18 years from 1999 to 2017? I get 20x, 10x, that's good, 40. Okay, some people are more optimistic, that's good. 64, okay. So I think here the numbers are, wow, somebody is very optimistic, 100x. That's good. It's good to be optimistic. Okay, maybe I didn't tell you all of the assumptions. So there are assumptions that go into this graph over here, like assumptions that would go into every graph. So the assumption here is we're not looking at fancy memory here. We're not looking at something like high bandwidth memory that's used in GPUs, for example, which is really expensive but low capacity. That's a different trade-off point. That memory is not commodity today. Maybe it will become commodity in the future. We're looking at DDR memory that's used in, for example, your cell phones, laptops, desktops, data centers, ... And that memory bandwidth has not improved as much. In GPUs, you can afford to have more bandwidth by paying more. So basically, in the commodity memory chips, it's about 20x, as you can see over here. It's much lower than capacity because chips are not designed for bandwidth as much, although this is an important consideration. Capacity is the most important consideration. And capacity is also the easiest thing to improve, by the way. Assuming your technology scaling continues, you're actually reducing the size of your cells and transistors by nature, right? By reducing your geometry, every technology node generation. So technology is on your side here. Moore's law is on your side. Of course, you still need to play a lot of tricks. In DRAM, I'm not saying it's easy. And we will discuss later on in technology scaling problems. In DRAM, manufacturers do a lot of tricks today. They actually etch the chip a lot in a 3-dimensional fashion such that they can put the capacitor inside there. So if you look at the aspect ratio, for example, of a capacitor and access transistor, in the third dimension, Z dimension, the capacitor is about 70 to 90x longer compared to the access transistor, which is really interesting to me, actually. So somebody asked, are we talking about single channel? Basically, we're not talking about not multiple channels. We're talking about a single DRAM chip. We're talking about if you take the DRAM chip and the raw bandwidth provided by that chip, we're looking at the raw bandwidth and the raw capacity. At the system level, it's a totally different thing. You can build a system that has much more bandwidth by adding more channels, of course, yes, sure. But the single DRAM chip's bandwidth is not improving as fast, okay? So this is the basic building block of the systems. Okay, and we will talk about how to build blocks of DRAM chips to construct bigger systems, of course. But in the end, you're limited by the bandwidth provided by this DRAM chip. Okay, and of course, you can always build bigger systems with more memory controllers, more memory channels, more chips, but that comes at other costs like power, efficiency, etc., which I'm not going to consider in this slide. Okay, that's a very good question. It's always good to consider the assumptions that go into a picture. Okay, let's talk about latency. Let me actually get your thoughts on what the, okay, before we talk about latency, bandwidth is actually easier to improve if you throw more money at it. Basically, you can increase the number of bits you can get out of a DRAM chip, for example. Today, you get out 8 bits per cycle, which is not a lot. You can increase that by 10x. It'll be a more costly DRAM chip, but you could do that. In a sense, some of the high bandwidth memory technologies do that by putting logic layer, by doing interposers between memory and logic layer. So you could actually pay more money and increase your bandwidth. And we will talk about the reasons of not doing that, how a DRAM chip operates, which is very similar to any other kind of memory chip also later on. Okay, and now let's talk about latency. How much do you think latency has improved over the course of these 18 years? Okay, I see numbers, 3x, 4x, less than 10x, 2x, 5x, 6, okay, 8, 7, okay, that's good. It's good that people are guessing. I'm afraid all of you are very optimistic in this case. You are pessimistic in capacity and you're very optimistic. You are almost in the ballpark in bandwidth and you're optimistic in memory latency, although somebody said not at all. So you're more pessimistic than what this data indicates over here. Basically, it's reduced by 30% or so. Basically, there are multiple reasons for it. One is commodity DRAM chips are not designed to reduce latency. The EDR protocol, at least the DDR chips, they're really designed for capacity. So the design mindset is here. The second reason is latency fundamentally is harder to improve, actually. We will see that when we talk about latency in general. It's really fundamentally harder to improve in a memory chip. I mean, it's not completely true, but compared to capacity, it's true. There are some things that you can do that you can improve, but people have not thought about it. So there are multiple issues over here. One is the design mindset. Design mindset is very, very capacity oriented. And the second is fundamental issues. Fundamentally, capacity is traded off for latency and vice versa. Okay, we will see this very, very clearly in future lectures. Actually, if you've taken digital design and computer architecture from me, you've already seen some of this when we talked about memory. I said that bigger is always slower, right? And I mean that. The bigger memory capacity is always slower. If you want to make things faster, you want to have smaller capacity. And no question about that. And we're going to see, of course, we're going to try to get the best of both worlds. Why is bigger slower? Because you have longer interconnects, right? And interconnect is really the evil for latency here. That is really what takes time to move the data around, move the voltage, move the electrons around, basically. Okay, so we're going to get back to this. But we know very well that applications actually demand more performance. Actually, if you look at the applications, this is, I showed you this picture before, I believe. But these applications, they're all employed in the field today. They're all important. Clearly, graph processing, we discussed briefly earlier today. It's very important in genomics, for example, in machine learning. A lot of machine learning frameworks are based on graph processing, for example. And these applications are bottlenecked by memory and different parts, different characteristics of memory at different times. So for example, in-memory databases are very much limited by memory capacity. Graph processing is very much limited by memory capacity. You don't want to go out to the disk to do the processing if you want to have a latency bound, for example, in your queries. A lot of data analytics is also a capacity, but there are also a lot of portions of this where they're limited by memory latency and memory bandwidth also. For example, graph processing is limited by memory bandwidth a lot because it does a lot of random memory accesses, as we will discuss later on. So this applications also drive a lot of the requirements. So you want some bandwidth. I didn't even put GPUs over there. I should put GPUs. GPUs actually are used for data analytics over here. But there are GPU applications, there are scientific applications that are extremely limited by memory bandwidth. Some of these data analytics are limited by memory latency a lot. So these applications are limited by a combination of all of these characteristics that I showed you in this picture. So we really want capacity, bandwidth, and latency. We don't want just capacity at the expense of other things. The question is, how do we get it? Okay, so if you look at the other end, which is the mobile end, let's say over here, browsers, this is inference accelerators, video playback and capture accelerators, which we're using right now through Zoom actually. Those are also limited by data and how fast they can process data. Sometimes memory bandwidth, sometimes memory latency, sometimes capacity. In fact, for example, Chrome, we will discuss a paper where we actually analyze Chrome a lot, which I use as my web browser sometimes. It's limited by memory capacity a lot actually. And as a result, the operating system does a lot of compression of the tabs. And that leads to latency issues in Chrome, which is very interesting. So these things are are also interrelated. Capacity and latency are interrelated. If you run out of capacity, it could cause a lot of latency and bandwidth problems also. So basically, applications are driving the requirements. Don't ever forget that. And they're the ones that are being bottlenecked because memory is critical for performance. Okay, let me give you some historical perspective at this point. Basically, didn't we know that memory is a bottleneck? We knew actually. It's not rocket science to figure out that memory is a bottleneck. And this is a paper that I will recommend. We will post this paper. This is a one-page paper written by a very senior architect, chief architect of alpha processors circa 1996, Dick Seitz. He actually designed a lot of the alpha architecture, and he led the team that designed the alpha processor at the time. It was the fastest processor of its time. And he wrote this paper. His opinion was asked as to what is the big bottleneck going into the future, basically. What should we be focusing on? And he wrote this one-page paper that was published in Microprocessor Report in 1996, after designing this fastest processor of its time. And basically, he said in this paper that we designed this processor. It's beautiful. It's nice. It has the capability to finish 4 instructions, 4 alpha architecture instructions every cycle, which are simple instructions, actually. But when we test this on this important workload, it happened to be a database workload at the time, it finishes on average 1 instruction every 4.5 to 4.7 cycles. So it has the capability to finish 4 instructions per cycle, but it's finishing 1 instruction every 4.5 to 4.7 cycles. So if you do the math, it's operating at 1/18th or 1/20th of its computational capability. Right? Basically, it's about 5%. Okay, 10 to 5%, let's say, if you would give the benefit of the doubt. Doesn't sound good. Most of the time, and basically goes on and says, most of the time it's waiting for data to come back from main memory. It's back-end bottlenecked, which is really the waiting for data part. Okay, and he finishes this article by saying, I expect that over the coming decade, memory subsystem design will be the only, and this is his emphasis, I didn't change anything over here except copying and pasting from the article, only important design issue for microprocessors. And I mean, he was very aggressive. He said only, right? I don't believe it's only, but I'm very close to believing that it's only. That's why we're talking about memory right now. And this is coming from a chief architect that designed many, many processors, including the fastest alpha processor of its time. This was a processor that was competing with Intel. But for commercial reasons, alpha was not successful in the end. And they also made some unfortunate decisions, perhaps, like they decided to scrap some backward compatibility in the alpha architecture. They had this VAX architecture, and they said, okay, we're going to get rid of VAX. All of the software that was running on VAX is going to run like a dog. We're going to transition to this alpha EV architecture, extended VAX, even though it's not extended VAX, it's really a simple architecture, reduced instruction set computing architecture. And they did that choice, and I believe that was one of the reasons why alpha was not successful in the market, because they essentially killed all of the software that was executing on their complicated, sophisticated processors. And as a result, they lost their software base by moving to a completely different ISA, even though they had very good processors. There were other reasons why they were not successful in competing with Intel, but we can talk about that later on perhaps. Intel, on the other hand, was quite successful, as you probably know, although it's having issues right now, clearly, because times are changing. But Intel was successful because they never said, okay, we're going to get rid of our software base and transition to a completely different ISA. And our existing software that was written for x86 is going to run slower. They never said that. I mean, there was a time where they moved to Itanium IA64, for example, that they quickly figured out that that was not a good idea. Or maybe the market was not ready for it at that time. It was, I believe it was actually a very bold move for Intel because they were innovating and they were trying something extremely risky. The extremely risky thing failed, but they never abandoned their mothership, which is really the x86 processor base. And as a result, they were extremely successful in keeping their software base running fast and benefiting. Okay, I digress. I gave you a reason why Alpha was not successful. This was not because these folks did not architect great systems. Overall, the company did not make, in my opinion, the right decision in terms of backwards compatibility. They basically scraped backwards compatibility and they said, we're going to go with a new architecture. That didn't work out well. Okay, but my point here is these folks knew that it was a memory, stupid. And this is the title of the article. So what does this mean? Basically, it's really all about the memory. And why is this interesting? So some people, there's a historical context to this particular saying also, basically. It's the memory stupid, right? These were election times in the US at that time, and Bill Clinton was running on a platform saying it's the economy, stupid. It's really all about the economy, basically, he was saying at that time. And I think in the end he won. But this was 1996, as you can see. And Dick Seitz over here is playing with that popular wording over here, saying it's really all about the memory, stupid, right? So we should get the memory right, basically. Just like Clinton was saying, we should get the economy right. Okay, so fast forward 10 years later. This is from my personal experience. This is from my first paper that I had written as a graduate student. And basically what we did in this paper was we showed that in the workloads that Intel was using to design its processors with, most of the time, the processor was waiting for memory. It's very similar to the observation that Dick Seitz made in 1996. We made it in 2003 in the modern workloads that Intel was using to design its processors with, and we had access to those workloads because we were collaborating with Intel on this. So it's basically the same thing. You can see this picture over here. More than 50% of the time, the processor is waiting for L2 misses. The green part is the computation part. Basically, it's finishing something. Basically, it's computing more than about 30% of the time. This doesn't mean that the computation is useful because there are some wasted speculation over here. Okay, so if you're interested, you can actually read our first paper, and we may talk about it later on in the lectures if time permits. Basically, we went ahead and said, okay, the processors are not designed to tolerate these latencies well, because clearly they're not tolerating them that well. Most of the time they're waiting. The idea was, can we actually do something in these waiting cycles? As opposed to stalling and waiting for data to come back from memory, can we actually pre-execute the program a little bit in these cycles, speculatively, and warm up our caches? And that was the idea we had at that time. It's called run-ahead execution. It was implemented later in some processors. That was designed by IBM and Sun, Oracle, and maybe some others that I don't know. But basically, that was the idea over here. And if you're interested, you can take a look at the papers. It was also published in a more accessible fashion over here. And this is the article that Dick Seitz wrote, basically. And I'd suggest taking a look at that article also. We will put all of these online. Okay, that's the performance perspective. And we've covered 1990s, 2000s. Okay, you don't believe Dick Seitz. You don't believe myself. I also actually, you may also be interested in reading this interview that talks about essentially the same thing and the historical perspective that I'm giving you over here, at least in paper over here. Okay, you may not believe me. You may not believe Dick Seitz. Jokingly, since everybody believes Google, I will quote something from Google over here. This is a paper that Google published in 2015. And this is also a paper that might be in your, well, that might be in your reading list soon. And essentially what they've done is a similar analysis to what we have done and what DigScience had done, but with more workloads. They basically looked at all of their data center workloads according to them. It's a huge diversity of workloads. And they found out that most of the time, the processor that they employ in their data center, which is really the cutting edge Intel processor of its time, Intel Skylake, I believe, is waiting for memory. These red cycles are backhand bound, waiting for data to come back from somewhere. The processor is doing useful work only in 10 to 20% of the cycles, basically retiring or finishing instructions. It's very similar to what the picture I showed you earlier with workloads that are 12 years ago, right? Nothing has changed in a sense, right? It's a bit sad, nothing has changed. And if you, I would recommend looking into this paper. It's a beautiful paper actually by Google. And they basically say half of cycles are spent stalled on caches and our workloads. And they basically suggest some solution directions. Some of, I believe many of them are incremental, but some of them are not so incremental. So it's good to look into that paper. But basically the takeaway is, clearly the performance of these processors have improved, but they did not improve as much as they should have because memory is still a bottleneck. That's the takeaway in terms of performance. So let me talk about energy and power. I have briefly talked about it in an earlier lecture, but I'm going to give you more data points here. By the way, any questions on performance? Performance is a fascinating topic. I can give you more data points, but we're going to do that later on. Is there any question, any burning question on this topic? Okay, nothing yet. And feel free to discuss. All of these things are discussion points, I think, that we can raise in Piazza. Okay, so energy and power is a huge system design concern today, actually. Let me give you some data points. So this is a paper by IBM, Lefergy et al. That was published in IEEE Computer in 2003. And they basically analyzed IBM's power systems at that time. I believe it was Power 5 systems, although don't quote me on it. No, it's not Power 5. Power 5 was not out there yet. I believe maybe it was Power 4. It should be Power 4 systems or the earlier generation, but I believe it's Power 4 systems. But basically, they analyzed IBM's cutting-edge power systems. These are big iron systems. This is huge rack of systems. You can imagine a data center, but these are things that are employed in banks, for example, to execute a lot of important code, transactional code, let's say. They analyzed the big iron system. They call big iron systems because these are extremely expensive. And they found out more than 40 to 50% of the energy is spent on the off-chip memory hierarchy. And at that time, this is 17 years ago, as you can see, the off-chip memory hierarchy included off-chip caches, off-chip interconnect, off-chip storage, off-chip DRAM, of which DRAM was a big part of it, actually, for those systems, because everybody wanted to run things in memory, not go to the storage as much as possible. So energy was really consumed on DRAM and the interconnect and off-chip caches, not as much in the storage. Storage was there for mainly archival storage. So basically, most of the, a good chunk of the energy was spent on the off-chip memory hierarchy as early as 2003. Okay, fast forward about 7 years later, these folks analyzed, I believe, IBM's Power 7 or Power 8 systems. And they found out, I think it has to be Power 7 if you look at the date over here. And they found out more than 40% of the system power, again, the big iron system is spent on DRAM, just DRAM, which is interesting, right? So now DRAM is consuming an ever increasing part of the power. That's true for GPUs as well. This is a study that was done by other folks on GPUs, cutting edge NVIDIA GPUs at the time, and more than 40% of the power is in DRAM. We did the same study on our own and we found similar things. Basically today, you can easily bet that half of your system power and energy is spent on DRAM main memory, including the off-chip interconnect, of course, right? You cannot consider DRAM without the off-chip interconnect because data is moved through that off-chip interconnect. Basically, half is a good ballpark, which doesn't sound good, right? Again, we are calling these computing systems, but half of the power is spent on off-chip components like DRAM. Okay, as we've discussed in the last lecture a lot, DRAM consumes power even when it's not used, so periodic refresh is a huge problem in DRAM, as you can see. And that's one of the reasons why we've discussed periodic refresh, because we want to get rid of that. Okay, there's a hand raised. Please go ahead and ask the question.
Yes, I'm a bit confused on what you mean by off-chip memory in this case.
So off-chip memory is, you have a compute chip, let's say an Intel chip, let's say, Off-chip memory is what gets connected to it. And DRAM chips are off the processor chip, right? Off-chip means off the processor chip.
Oh, okay. So anything that needs to go, needs to get outside of the processor, basically.
Exactly, yes. Either outside, it needs to go outside of the processor, or it needs to move data inside the processor, yes. But anything that's outside of the processor chip, yes.
Thank you.
Sure. Okay, so that's the energy part. And you've already seen this picture. This is basically energy cost of data movement. A sophisticated double precision floating point operation is 20 picojoules. A not so sophisticated one is about 1 to 2 picojoules, let's say. Okay, so even simpler adds are actually smaller. But a DRAM read or write is about 16 nanojoules. Of course, assuming some technology assumptions, and the situation is not as bad as that's depicted over here today. But today, a memory access consumes somewhere between 100x to 1000x the energy of a complex addition. So there's a 2 to 3 orders of magnitude difference. And that's one of the reasons why memory spends, there's a lot of energy spent on memory. Refresh is one reason, clearly. Data movement is another reason, right? And there's more, actually. And we've actually recently, this is more recent data than what I've quoted so far, recently done this study, and I will also mention this, and we're going to look at this later on. Based on this recent study that we've done together with Google, more than 60% of the entire system energy is spent on data movement in mobile workloads. And we're going to talk about how to mitigate it also. And I see this as a huge waste in devices in general, certainly in mobile devices, but certainly, but also in data center type of devices as well. Why waste if we can do something better? And we're going to talk about that in this lecture, how to do something better. Okay, that was energy and power. Now let's talk about scaling, because scaling is going to affect pretty much everything over here: capacity, bandwidth, predictability, latency, energy and power, and other things also like security, reliability, etc. So what is scaling? Scaling basically is you have a cell, an electronic cell, and you want to reduce its size. And once you reduce its size, its properties improve. Bob Denard, who's also the inventor of DRAM in 1965, also wrote the seminal scaling, technology scaling paper on this, basically examine the characteristics of how much performance scales and power scales as you reduce the feature size of a transistor, for example. Okay, we're not going to go into the paper. Hopefully we will put it up. My TA should put it up based on my reference to it at this point. We don't have the reference on the slide, but please do put it up. If people are interested, they should look at it. But this scaling, technology scaling, has provided many benefits in logic as well as DRAM. Now we're focusing on memory, and DRAM is an example memory technology, right? But basically you get higher density in terms of cells. In logic, you get higher density in terms of transistors. You get lower cost, which really helps Moore's law, because now you have lower cost of a transistor and you can put more transistors on a chip, and you get lower energy, which is really great, because basically now by reducing the size of a cell, a DRAM cell in this case, but a transistor, a logic gate in some other cases, you're getting a lot of benefits. Now the problem is this is becoming much more difficult. What does this mean? You have some feature size of a DRAM cell, let's call it Y. And you keep reducing it over technology generations. And at some point you hit a value X, and at that value X, it becomes difficult to reduce the size more. Why? Because retention becomes a problem, because row hammer becomes a problem, because you get other sorts of noises, because energy starts increasing for some reason, because scaling doesn't hold very well, because your transistors becomes more leaky. You have a lot more leakage, static leakage in your transistors also, not necessarily refresh problems, but just leakage energy problems. These sort of things can happen as you reduce the size of a transistor and a capacitor a lot. And that's what's happening in DRAM today. And you can see that I use a hard word ending over here. DRAM technology scaling is ending. Ending is always a hard word. People have predicted Moore's law would be ending in 5 years, 20 years ago. Maybe 30 years ago, actually. People have been predicting that Moore's law is going to end 5 years later. And I still think that it's 5 years away. So actually, I don't think Moore's law has ended yet, because people are still scaling transistor density. It's become more difficult. No, absolutely no question about that. And there are other issues in Moore's law, I think today. Basically, lithography is a big issue. How can you etch things on a wafer? So it has become limiting. It's limiting the scaling today. And also energy has become a problem in Moore's law, for example, in logic and transistors. As you scale the size of the logic, now energy is not reducing as much because you cannot reduce the voltage as much because you hit the limits in terms of how much you can reduce the voltage. Otherwise, the transistors will not operate. As a result, your energy is not scaling with the size of your transistor. And as a result, the motivation for scaling is reducing also. So once that motivation goes away, we can perhaps declare Moore's law ended. But I don't think that motivation has perfectly gone away at this point. It's become more difficult, but people are finding ways to actually get more out of scaling with more effort, certainly. Okay, so this is a more general treatment of scaling. But in terms of DRAM, the scaling is ending actually because people are actually a lot more worried. DRAM has reached its limits because of the capacitor much faster than transistors themselves. So capacitor is much harder to scale because it's a much more leaky structure actually. And we will discuss this a lot more as we go along. But basically, so I have an anecdote over here. When I talked about DRAM's technology scaling in International Memory Workshop, actually it was in MEMCON for the second time. MEMCON is an industry workshop on memory. And I was invited to give a talk over there. And I basically put the slide up saying DRAM technology scaling is ending. And everybody essentially seemed to agree with that. This was not a controversial opinion. Even though when we were writing about all of this in academia, we got some pushback saying that, oh, where is the evidence, right? And then we later gave a lot of evidence in terms of retention times, as well as row hammer, as we will discuss. But basically, this is, I believe, a well-known fact right now that both industry and academia have to deal with. Okay. So there's an X nanometer here. The question is, what is X, right? We don't know at this point, but we know where we are in terms of X nanometers. In a little bit, I may ask you some questions actually related to where we are to see just how much you know about DRAM. You don't need to know anything actually, because we're going to cover things. And this scaling problem is not limited to DRAM. As I said, logic suffers from it. It's going to suffer even more. But other memories also suffer from it. Flash memory, for example, suffers from it. SRAM suffers from it. Any memory will suffer from it. But let's take a look at DRAM because we're really bottlenecked by DRAM today. So as I mentioned earlier, DRAM stores out charge in a capacitor. It's charge-based memory. And this capacitor must be large enough for reliable sensing. And all of the access structures must be large enough as well. So this access transistor is really more part of the access structure. And that needs to be large enough for low leakage and high retention time, as well as good sensing. And all of this, everything else should work also. Basically, whenever you need to read DRAM, it goes to the access transistor, and you need to sense what comes out over here through a specialized sense amplifier, which is really costly, actually, as we will see later on. Costly compared to the size of a cell over here. So the size of a cell has been reduced a lot. So this is actually, and later I will show you another picture over here. But basically, it doesn't look two-dimensional like this. You have this transistor, let's say in the planar XY dimension. But now imagine this capacitor being etched into the Z dimension. So in a sense, you have this transistor, and in the Z dimension, in the three-dimensional view, a capacitor's length is about 70 to 90x the length of a access transistor actually today. I will show you a picture of this later when we talk about DRAM in a little bit more detail. So that's the extent of things that are happening in DRAM today. To be able to make this capacitor work, what the DRAM manufacturers are doing at of course, low storage area, that's important. To be able to make that work, they're really etching into the wafer a lot in a three-dimensional fashion. It's not exactly a three-dimensional stacking technology. It's really a single wafer. What they're doing is really etching the single wafer. And at some point, this may become unsustainable, right? Okay. So basically, these are some of the challenges that manufacturers are facing. And this is true for flash memory also, which we may talk about later on. But in DRAM, there's this body, International Technology Roadmap of Semiconductors, that basically pushes out a report every year. They renamed themselves recently, but okay, that's beyond the purpose. They basically push out a report in terms of technology outlook. And their reports are very interesting because they talk about some technologies like future memories, like racetrack memory, etc., and their characteristics, how good they are, how bad they are today. And also they talk about existing technologies like FinFET or some other logic technology. And they talk about what are the scaling challenges. And they clearly talk about DRAM. Obviously, everybody cares about DRAM. Since the DRAM market is huge, actually, and everybody buys DRAM. But basically, they said in 2009 that reducing the feature size of a DRAM cell below 35 nanometers is challenging. And they said we will reach 35 nanometers in around 2013. And that was approximately true. And they were also true in this case. It was challenging, actually. But today, manufacturers actually pushed a lot. And today we're at a point where the feature size is much lower than this. So let me give you that hint. So what do you think is the feature size of a DRAM cell, a cutting-edge DRAM chip today? You can guess, like you've guessed in the previous times. I'm waiting for guesses. This may be a hard guess, of course, because you may have no idea. But you have an idea, perhaps, that we're below 35 nanometers today. I will give you that. And logic is around 7 nanometers today, right? You know TSMC is able to manufacture 7 nanometers logic. Now, these things are not comparable because people actually use different definitions of feature sizes. Even in terms of different logic technologies, they use different definitions. But in logic, we're much better. It's on 7 nanometers. In DRAM, where are we? Okay, let me look at what people have put. 20, 16, 20, 20, 25, 16, 20, 10 nanometers. So the person who put 10 nanometers is optimistic, clearly. But today, we're actually around, yes, 16 to 20 is a good guess. We're actually around 16 to 17 somewhere, basically. Around that, in the cutting-edge DRAM chips. So we're well below 35 nanometers, which was the point ITRS said it was challenging to go below, which was correct. And it became much more challenging after 35 nanometers. We're not at 10 nanometers yet. The question is, where can we scale down to? I actually like asking this question to DRAM designers whenever I visit DRAM companies. And the lowest I got was 7 nanometers. So today we're at 7 nanometers in logic. Okay, apples to oranges comparison, but it gives you an idea. But basically, people are not optimistic that we can go below 7 nanometers. And let's see, of course, people will push for it because DRAM is a major technology, and it's, regardless of its deficiencies, it's still a good technology to be employed because it has not, it's difficult to replace it in terms of its characteristics. But let's see the future. But as I showed you this slide earlier, charge memory is difficult to place charge and control it. Okay, is there a lower bound from physics? That's a great question. And I don't think I'm qualified to answer that question because I don't think I'm an expert in device physics. But that's really a good question to ask someone who knows device physics. And if you're interested in doing some research in that area, there are papers related to it, although it's very hard to find cutting edge papers related to it. But I believe there's a lower bound in physics, no question about that, because at some point, if you cannot move an electron, or if you cannot sense an electron, then probably it doesn't make sense to store it also. It doesn't make sense to go down to that feature size. But of course, I don't know what that lower bound from physics is. And also it's dependent on the sense amplifier you can build, I think. At some point, to sense, let's take this TOEFL experiment. You have single electron in the capacitor. Maybe it's extremely leaky, but you found out ways of dealing with that leakage somehow. You have the single electron. Now, how do you sense that single electron with no noise or with little enough noise with a good sense amplifier? Basically, the question boils down to that. So in the end, device physics limits something, but also architecture and circuits and devices you can build for sense amplification limits things also. If you can build a device that can sense that electron, maybe you can pull that limit to a single electron. If you can build something that can sense half an electron, which is also an interesting thought, maybe you can do it, right? This is the push of our technology scaling. Again, it really takes creativity and hard work to build those devices that sense electrons. And as a result, sense amplifier is one of the most complicated parts of a DRAM device today. It's an analog part, but also there's a digital component to it. But that's the best answer I can give you related to that. So I don't know what the limit is today based on current devices from a device physics perspective in terms of nanometers, let's say. But I believe, I'm hopeful that there will be people who will be pushing it to the edge such that devices are built. But at some point, those devices may be too costly to build. a device to sense a single electron may be too costly to build to operate at high reliability, for example. Okay, and that I think ties back nicely into the slide that I stopped at. Basically, these devices are not easy to build because we're dealing with charge, and charge is expressed in terms of electrons over here. Essentially, you trap charge in the floating gate in flash devices. It's also charge-based memory. In DRAM, it's a capacitor. And data retention and reliable sensing becomes difficult as the charge storage unit size reduces. You either need to make the sensing structures much better, much more tolerant to noise, or store more stuff such that you're less vulnerable to sensing issues. That's the idea over here, and retention issues also. So we're going to see that this is difficult. Okay. There's evidence in the field that as memory scales, it becomes unreliable. Scales meaning the feature size reduces, so you can pack more cells into a given area. So this is a study that we had done with Facebook. I think this is the latest study in the field. There might be others that are actually from national labs in the United States. I think they're all similar in terms of its results. But basically what we've done in this study is we worked with Facebook to analyze all of the memory errors that they have in the systems that they have. So this is actually very interesting because it turns out Facebook has perhaps the largest data centers and as a result, largest amounts of memory distributed across the world. Now, ignore all the other issues with Facebook. There are a lot, I believe there are significant privacy and security and, I don't know, human future related issues in Facebook. But clearly, a lot of people are not concerned about it, and they bank on putting their data in all of this memory. So we were able to, thanks to their help, we were able to do the study that we did. We basically analyzed all of the memory errors that they have, and this is a lot of memory. We cannot unfortunately talk about how much memory and how many servers this is, but this is a lot more memory than what has been published in related studies before. We cannot write about it because it's confidential, because Facebook had feared at the time that their stock price would be affected if we reveal the size of the memory that they have. If we reveal the size of the memory that they have, anyone can actually calculate how many data centers or how many servers they have in data centers across the world, because their server designs are actually open sourced. You can find what their server designs look like in the Open Compute project, for example, even today. But basically, it's a lot of memory. And you can do this correlational study in production data centers. And this is the correlational study that we have done. We recorded all of the memory errors that the servers experienced during the course of 1.5 years or so. And we basically looked at what fraction of the servers get errors with 1 gigabit chips. Yeah, exactly that. And with 2 gigabit chips and with 4 gigabit chips. So the server employs 4 gigabit DRAM chips, 2 gigabit DRAM chips, or 1 gigabit DRAM chips, and you see the error rate that you see on the server. And turns out, it looks like this basically. Basically, because the chip density increases, it's correlational. We cannot say because, but clearly there's a correlation between the error rate that you get and the chip density that you have on the server, where you get the error rate. So you get a lot higher errors in chips with higher density. So somebody asked the question, very good question, how is the memory failure rate measured? Please refer to the paper. It's actually a normalized measure over here, because we have to normalize it, because if you think about this is a different population than this, which is a different population than this. So what we cannot do in a production server is take exactly the same server and measure the failure rate with some metric, which is really failures per second, let's say. That's one metric actually. We use that, but it's not enough. We cannot compare that. We need to normalize it to some baseline servers, because now we actually look at, we cannot take out the chip while it's in production and replace it with 2 gigabit chip and then replace it with 4 gigabit chip. That's not what we can do. And as a result, we need to treat statistics extremely carefully over here. So this relative server failure rate measure is something normalized to a known population, basically, that we can, where we know the failure rate. So take a look at the paper for detail. It's not an easy study to do in the end. But if you do the study correctly, this is what you get. And other people actually replicated our study on other types of data centers, clearly not on Facebook's data centers. And they've seen similar trends later on. But basically, as you employ a higher density DRAM chip, you get more errors. Okay, and this is because the cells are closer to each other. The memory chip is less reliable. And we examine a lot of reliability characteristics in this paper. If you're interested, I recommend looking at this paper. There are a lot of reliability characteristics that are examined in this work. So take a look at it, and I'd be happy to recommend more papers. I don't think we're going to go into a lot more detail in this lecture about this. But this is correlational studies. Google had done actually an earlier study in 2009 where they found similar things, but their study had some issues. For example, they double counted some of these errors. So exactly the question your fellow student asked was very valid. If you start double counting some of the failures, that's not good because it may be caused by the same cell. So in this case, we were very careful in terms of not double counting errors. But their study was actually seminal because it was the first study that studied Google data centers. It was in Sigmetrics in 2009, I believe. But we essentially replicated and strengthened the methodology that was done. And we looked at real applications, real production applications that exercise systems in Facebook in this case. Okay, so clearly reliability is reducing. And as I mentioned to you last time, we had the suspicion even before we started working with Facebook, for example, and we built a lot of infrastructure, FPGA-based infrastructure to test memory chips. This is where Rowhammer was actually really discovered, and we did a lot of studies. We will talk about this infrastructure also later on. There might be a lecture from Hassan related to this actually, because Hassan is actually the person who took this infrastructure and took it to the next step, made it easily programmable by many people such that it has a C++ API, and we open source this infrastructure. So it's an open source memory testing infrastructure that many people employ, and we're going to talk about that actually. Many people in companies as well as academia also use this infrastructure today. And if you're interested in using this infrastructure for projects, we'd be happy to support it, and you can look at this paper. But with this infrastructure, we were able to study many things. And as I said, I gave you examples of studies that we've done in retention time, which is really, really important. And we did talk about that a lot in the last lecture. And we did talk briefly about Rowhammer. If you have this sort of infrastructure, you can find new issues like Rowhammer. Basically, you can predictably induce errors in most DRAM memory chips. I'm not going to talk about this in more detail since we're going to have a bigger lecture dedicated to a case study of Rowhammer, because this is very indicative of what is going to come into the future, in my opinion. And this is also fundamentally extremely interesting because, as I mentioned, we had published our original paper saying, oh, you can predictably induce errors in most DRAM memory chips in 2014. For some time, no one cared. In 2015, Google published their paper saying, oh, this actually could be a widespread system security vulnerability. And then in 2016, everybody was actually very interested because this problem can actually, these bit flips that you can predictably induce into Rowhammer is actually something that may make us forget even software vulnerabilities, right? Okay, over time in 2000, this was the paper 6 years ago. We're going to cover this actually. And this is the really, now I'm giving you the reliability and security perspectives of scaling. And Rowhammer is a really, really fascinating, real example of technology scaling problems that DRAM is seeing today, bit flips basically that you cannot control. And this is becoming worse. And this retrospective covers it, as you can see over here. And as I mentioned in the last talk, in the last lecture, maybe people were thinking, okay, Rowhammer's gone away, but it's really not gone away. It's really still a problem, as this paper has showed, with fundamental observations on real devices. And the manufacturer and the solutions that manufacturers, DRAM manufacturers say are Rowhammer free. Basically, manufacturers actually advertised recent DRAM chips saying, oh, we have a solution to Rowhammer. Internally, these are not vulnerable to Rowhammer. Okay. And they never said anything beyond that. Basically, they never said how the solution works. They basically tried to provide security by obscurity, if this is something that people have tried a lot, but usually security by obscurity doesn't work very well, because there are a lot of very smart and creative people out there who try to actually attack you. And we were the white hat people in this case. Basically, we wanted to actually test this hypothesis, which was not backed by any real theory, if you will, by DRAM manufacturers saying that, okay, these are Rohammer free, and we tested them, and we basically were able to construct attacks that prove that that hypothesis is false, meaning these chips that are advertised as being protected against Rohammer completely are not protected. That's why Rohammer is very interesting today, because of the scaling problem, everybody's trying to find solutions, and clearly not all solutions are good enough. And I think finding solutions is also a very good reason why we should investigate the problem. In fact, that's perhaps the more important reason to investigate the problem, and maybe some of you will find good solutions to Rohammer that will finish the problem, if you will, under certain cases. Okay, so we're going to talk about Rohammer in the next slide, and we may actually discuss some research problems also, like can we identify chips that are vulnerable to Rohammer by some testing or not. Okay, so essentially, there's all this evidence in the field now showing that DRAM scaling has already become increasingly difficult. And we have been publishing a lot about this. I'm going to give you some more examples. So it's difficult to significantly improve capacity, energy, and reliability and security are already threatened right now. And as a result, one solution is clearly designing better DRAM, and we should look into it, designing better memory controllers. We discussed that. But emerging memory technologies are also very promising, and we're going to talk about that. So 3D stacked DRAM is very interesting. Reduced latency DRAM is very interesting. Low power DRAM is very interesting, and non-volatile memory, of which there are many, many kinds actually, is very interesting. And I've given you the most salient upsides of these different technologies, some of which are based on DRAM, as you can see. But unfortunately, there is no technology that has only greens. Basically, all of them provide a trade-off, and these are the most salient trade-offs, basically. For example, in 3D stacked DRAM, bandwidth is traded off for capacity. And maybe you get logic computation capabilities. In reduced latency DRAM, again, latency is traded off with cost and capacity. Lower power DRAM provides you higher latency, higher cost, and non-volatile memory, depending on the memory technology, even though you may get larger capacity, you may also get larger latency and endurance problems and dynamic power problems. So we're going to talk about a lot of these technologies, actually. We'll have a dedicated lecture on emerging technologies, for example, which is, I think, fascinating. But suffice it to say at this point that no memory technology is green at every metric we want it to be green at. All memory technologies provide a trade-off. As a result, a picture like this makes a lot of sense. Basically, this picture I drew a long time ago, but industry has moved into this picture right now, I think. There's a major trend, which is main memory is becoming hybrid. And even on-chip memories are becoming hybrid. Main memory is an interesting example because we're very much bottlenecked by it today, clearly. So what does this mean? This means that because no single technology is green at every metric, why don't we put different technologies that have different greens and also different reds? And now design the system, hardware and the software, cooperatively so that you manage the data allocation and movement such that we achieve the greens as much as possible while avoiding the reds as much as possible. Now that sounds great, right? This hopefully gets the best of both worlds, the greens, while avoiding the bad parts of both worlds, the reds. And that's the idea over here, hybrid main memory. And this is being employed today with hybrid DRAM, going in, for example, you can have high bandwidth memory, but you can also have DDR memory. High bandwidth memory is fast, small, high cost, high bandwidth, low capacity. Low bandwidth memory or DDR memory, low bandwidth, high capacity memory is large, low, high capacity, low cost, but it's lower bandwidth, and it's actually energy of high bandwidth memory is more than energy of this. So there are trade-offs. So I can put high bandwidth DRAM and commodity DRAM over here. That's a hybrid main memory that exists today. That kind of system exists today, and you can actually do experiments on it. And the best way of taking advantage of it is, again, across the stack, algorithms to devices, in my opinion. Or you can put DRAM and phase change memory, which makes the trade-offs look like this, even more salient, as you can see, because now you have a durability positivity here, but this one wears out. That doesn't sound good, right? How do you manage this memory technology? Okay, so we will talk about this later on, but this is an idea to give you the current challenges and opportunities. This is a challenge to build it, but it's also an opportunity to make the memory system more scalable. This way, you're less bothered by the memory technology scaling concerns of any memory technology, because you're putting many memory technologies and hopefully using them in the best ways to get the best of all worlds. So overall, your system may be scalable, even though individual technologies may not be as scalable. So this is a very system level approach, as you can see. And you can adapt the algorithms to the characteristics of the devices that make up your technologies. So the sky is the limit in this case, which is really exciting, I think, because there's a lot of opportunity. But it's also a challenge because there are a lot of difficulties here, right? Systems are not used to hybrid memories. Maybe your virtual memory system doesn't support it at the higher levels of the stack. Your applications may not be aware of memories, and it may be a good idea if they're aware, potentially, or at least if they communicate their requirements. Or your memory controller may not be designed for it yet. So there are a lot of issues spanning across the stack to make this work. So it's fascinating. Again, this kind of picture was not there in 1990s or early 2000s. This picture I drew actually again in 2010, I think, in a keynote I gave on main memory. Okay. So I think one foreshadowing I will have is clearly there are a lot of challenges and there are a lot of opportunities, but I think a lot of the challenges could be solved and new opportunities can be enabled if we actually make the memory controllers more intelligent. So if you look over here, they're memory controllers. I depicted two over here, but this could be a merge controller also. Basically, if you make these controllers more intelligent, such that it can understand the properties of the data, both at the low level, for example, which data is being touched, which data has more locality, but also at the high level. What are the requirements on my data from the applications? If it knows all of that information, it can actually schedule things better. It can say, oh, this data is not important to this application, so I'm going to put it in memory that is slow, or maybe it's not completely reliable because I know that the application is not going to care as much about the reliability or guarantees on this data. So that makes life a lot easier, but it requires an intelligent controller, right? Intelligent controller to decide where should the data be placed based on the characteristics of the data and also the characteristics of the devices. The controller needs to have intelligence in terms of what the devices look like, what their characteristics are, what their trade-offs are, and it needs to be able to make those trade-offs nicely. But also it needs to know the characteristics of the data and the applications and the requirements such that it can map the different requirements to different trade-offs over here. So this kind of controller doesn't fully exist right now. It's a research problem, but it's really important going into the future because people are designing this sort of systems. And again, this is an across the stack problem again, right? You need to communicate to the controller from the software. You need to communicate to the controller from the hardware. And the controller needs to manage things in some way. Because in the end, you need to have a controller to manage memory. You can also think of this controller being as part of the software. There's an operating system component over here that I have not depicted. But the operating system, memory management, garbage collection, virtualization, virtual machines, all of those actually play a role in the management of the hybrid memory. If they're aware of the characteristics of the application, as well as aware of the characteristics of the controllers, as well as devices, they can make much better decisions. So we need intelligent controllers in the software as well as hardware, basically. So this is not just about hardware, as you can see. Although I think in the end, controllers need to be coordinated across the software and the hardware as well. Okay, so industry is writing papers about it too. I mentioned this paper earlier. So basically, scaling problems are very difficult in DRAM today. As a result, two companies that don't normally talk to each other have come and written this paper in 2014 in the memory forum we organized, Samsung and Intel. And they basically said we're having a lot of challenges. They didn't want to talk about Rowhammer at that time, unfortunately. Well, fortunately for us, maybe, because we worked actually with some of them, like Intel, to actually look into Rowhammer-like issues as early as 2012. And then we published our paper in 2014. At the same time, this paper was published. This was a nice synergistic paper with all of the papers we've published in DRAM retention, for example, showing that clearly there are issues in DRAM process scaling, and we should have some more intelligence in the memory controller. So we're going to talk about this intelligence in the memory controllers aspect a lot in the course, because this is something that's going to be more and more important going into the future. And not just memory controllers, but all of the controls in the system should probably be intelligent going into the future. Cache controllers and disk controllers, solid state drive controllers and network interface controllers, etc. Okay, so this is another paper that I would recommend, but I'm going to refer you to this multiple times in this lecture. So that shows you the importance of a paper, I think. And this is one of the rare industry perspectives that got written actually. And again, as I said, it's unconventional because I do not know of any other paper that got written by Samsung and Intel co-authors at the same time. These are actually two co-authors, meaning Samsung DRAM design team plus Intel memory and memory controller teams got together and wrote this paper. It's not like one author who used to be at Samsung moved to Intel and now they have double affiliations. No, that's not the case. It's truly two different teams that come together and write this paper. Okay, and they felt it was important to write this paper to push it out. Okay, so there's an orthogonal issue, which is really the memory interference issue. That's also very important. That's really orthogonal to everything else we talked about. And this is an important issue that needs to be solved because this makes memory systems more predictable potentially or less predictable. And the issue is basically what we talked about in memory performance attacks. Basically, cores or accelerators or agents share the same medium when they access physical main memory. And because they share the medium, they interfere with each other when they access shared main memory. And as a result, when they interfere with each other, they can deny service to each other, they can cause unfairness, they can violate each other's latency guarantees, bandwidth guarantees, performance guarantees, etc. So there are many issues over here as we discussed with memory performance attack. And uncontrolled interference leads to many problems: quality of service, performance, SLA violations, etc. Energy in the end, because people may decide, okay, I'm not going to run many applications in multiple cores, or I'm not going to turn on this accelerator while I'm running this core, right? In the end, your energy would be compromised. And this is something that's completely independent of what your main memory looks like. As long as you have a shared medium, your main memory could be DRAM, phase change memory, it could be an SSD, it could be storage, it could be a hybrid combination of many of these things, you still have the same problem. So it's a higher level problem. And we need to solve this problem also because this is really important going forward because, as I said, this is easy. Core counts are increasing. We can easily add stuff over here. We can easily put applications over there. The bottleneck is really here. The bottleneck is really here. And how do we actually provide predictable service to those things that we can easily put over here is a key question. And we're going to talk about that. But this is a foreshadowing of the challenges on the opportunities. It's a challenge, clearly. How do you do it efficiently is a challenge. But there's also a huge opportunity. Now we can design much more predictable systems because we never really fully tried to do that before, except for safety critical cases. So if you look at safety critical cases, safety critical processor design, for example, in automotive cases, it's very conservative. Basically, you don't even have dynamic systems over there. You have static code. You completely statically schedule it. Assume that that's the only thing that runs in the system. And that thing is the only thing that runs in a core, maybe too powerful for it, to ensure that your safety criticality is not violated. At least you hope that that's what's happening in automotive industry and maybe airline industry. Although there are really interesting reports related to Boeing 787, for example, which you may want to read, that maybe some of it is not happening fully. Okay, but assuming that that's happening, and that is honest, that's the honest case where what should be honestly happening, I think. You have a safety critical system. Somebody needs to design that system such that safety is the highest priority. Okay, but it comes at a huge cost. So if you look at these automotive systems, basically the cost is efficiency, right? You cannot run multiple things at the same time. The automatic brake controllers cannot run with, I don't know, your other engine controller at the same time. You lose a lot of efficiency. That's why you have many different controllers all over the system. And they're not, they're also not very reconfigurable or patchable because safety is the highest priority and reconfigurability adds some problems. So your software is not fully upgradable in some of these controllers. So there are many issues over here that lead to it. So if you actually design the system from the ground up such that safety or predictability like this is one of your first level criteria, then actually maybe we can actually come up with much better safety critical systems as well in the end. And actually some of the work that we have done in quality of service predictability attracted a lot of attention in the factory communities. These are basically assembly lines. You have in the factory, again, you have a safety critical systems. You need to actually make sure that a robot moves when it's supposed to move. And it takes some certain amount of latency to actually move one piece to, from one location to another location, right, in a factory. And this is mass manufacturing, clearly. You don't want that robot to be late, otherwise everything gets backed up, or and even worse, you may have other problems, right? So when we were talking about quality of service, actually, there was a lot of interest in using multi-core systems in these robots control systems in factories, such that you can actually get predictable performance and latency guarantees. And I think that's another example, safety critical area, where we can enable much better systems in a much more efficient way and a much more dynamic and configurable way. Okay, this problem is getting worse a lot. Something like my cell phone, for example, looks like this, and even worse, in the sense that we have heterogeneous agents, CPUs, GPUs, hardware accelerators. We have heterogeneous memories, and they're going to become even more heterogeneous. And there's main memory interference between all pairs of them, or not just pairs, but all choose n of these. As a result, this design is becoming a bigger problem, right? How do you allocate resources to heterogeneous agents to mitigate interference and provide predictable performance is becoming a much more difficult problem. And this is already a problem in a cell phone like this. We have lots of accelerators, GPUs, CPUs, and that different amounts of sharing. In the end, main memory control is literally at the center of everything in these devices. So we really need to design main memory, and main memory is becoming much more important going into the future. Thus, this is a huge challenge. How do you design these? But also a huge opportunity, because these are things that need to be designed in a good way, and we have an opportunity to actually make a difference. Okay, my foreshadowing again is main memory needs intelligent controllers. If you actually want to understand how to design a better controller over here that obeys the characteristics of these things, well, we really need intelligent controllers over here. And we need to understand the characteristics of different applications, different accelerators, different memories, and the controller needs to be intelligent enough to do better scheduling. And maybe it needs to specialize its scheduling to the characteristics of different applications. So memory controller needs to be intelligent. So this is another foreshadowing. Okay, I think we're just on time actually. Oh, we have 3 more minutes left, but I've covered everything I wanted to cover. I wanted to cover challenges and opportunities. There's actually a lecture 3C right now, which has become lecture 4A, which is really an overview of the solution directions. So I have not fully covered the solution directions, although I've given you glimpses of it. So we're going to cover that tomorrow, and we're going to start with the basic issues like Rowhammer. As I said, since it's a fascinating topic that's really occupying a lot of industry today, from software to hardware. Companies like Google and Microsoft and others are worried about it, not just the DRAM manufacturers, as you can imagine. Okay, so this is a place I will stop. If there are questions, we still have 2 minutes. If there are no questions, we can call it early. Okay, there's a raised hand, please ask.
So I was wondering, you mentioned like the difficulty of scaling is retention. So I was wondering if there is any potential research on giving more leeway in terms of retention, but improving or researching ways where memory recovery can be done better or faster.
I see. Yeah, that's a good question, basically. Yeah. So basically, we've seen research that tries to make retention less of a problem in the last lecture. We didn't talk much about what happens. Okay, you get retention errors. Even all of your techniques may have failed, or maybe you didn't employ all of those techniques. You get retention errors. Can you recover faster? I think that's an excellent question, actually. And I think there needs to be more research in that area. There's some research I can point you to. Actually, some of our papers try to do some of that. When you get an ECC error, can you try to figure out where that ECC error happened? And once you figure that out, maybe that could be used as a basis for recovering from that ECC error. So that's one thing. And I would recommend you take a look at, for example, Minesh's 2020, Micro 2020 paper. It's called Bit Exact ECC Recovery. I think that starts a point where you could potentially do error recovery when you get an error. Clearly, to be able to do that, you need to figure out that there is an error to begin with and something went wrong. Maybe you do recovery offline or online. So I think that's a very valid point. There's less research on the DRAM end. There's more research on the flash end, actually. In the flash end, for example, there's a lot of effort into understanding what happens in a failed SSD drive. If you failed, now let's try to recover the drive. Some of those techniques are not new, but some of those techniques are also new. Some of these failures happen because of data retention, because that was not satisfied. And we actually looked at a lot of data retention in flash memory. That's one of the, that's going to be one of the readings later on, potentially, when we talk about flash memory. But we have a recovery mechanism also. That's an offline recovery mechanism. Okay, you got an error, maybe a retention error. How do you recover offline? And it turns out one of the interesting ways of recovering happens by inducing more errors into the flash chip. So let me give you the basic idea very quickly because I find it fascinating. Okay, you got an error, you recovered. Let's induce more errors and examine the properties of different cells. Okay, before that you checkpoint the flash drive so that you don't lose the data that you have. Okay, let's induce more errors. Now, once you induce more errors, you understand the different properties of different cells. And based on that, you can guess which cells were more vulnerable when you got the error. It's a guess, of course. It's not perfect. It's probabilistic. And now with that information, what you can do is you can go back and try to correct some cells at the checkpoint, meaning at the point you actually got the error. Because you know some of them are errorful, you corrected them. Some of them you couldn't correct because clearly your drive failed. Now you go back on all of those cells and try to figure out which ones could have been subject to failure, and you correct them based on the information that you gathered. You could actually do even more sophisticated techniques like machine learning. You could actually learn, in my opinion, train a neural network. I have not seen anyone do that, but you can potentially train a neural network based on all of the errors that you've seen offline, and you could use that. You could feed that to do recovery. But even with a simple recovery mechanism that I just said, that doesn't use a neural network, we saw that you could actually reduce the error rate by more than 30%. Basically, you can recover from 30% more errors, and you can keep going a little bit more. You can increase the lifetime of your device. So hopefully that gives you an idea. So I think that answered your question, right?
Yes, thank you.
Okay, cool. But I like this thinking. It's always good to ask, okay, maybe you don't solve the problem in the way that was described in the lecture. Maybe there's some other way of solution. And that's, I think, a good way, actually. In the end, data recovery is extremely important, I think. And that's an area of research that people should look into more. Okay, any other questions? Now we are 3 minutes over time. Okay, if there are no other questions, let's stop here. We're going to start at 1 p.m. tomorrow with some solution directions, and we're going to continue with the rope hammer. Okay, have a good rest of your day. See you tomorrow.